Hi, good morning, everyone. I guess we'll get started. So the rest of class, they should be able to check on the video later if you missed the first part. Okay. So if you just can send everyone say good morning. If you haven't done so, then I will check that. I will trace that later for the attendance. Okay. So we'll get started. Let me share you guys my PowerPoint slides here. All right. So let me put in the full screen mode. Okay, so we will still be checking chapter 23 here. So a few reminder items here to start with. So lab 8 this week we'll be doing standing wave. Okay, so if you get a chance, you can go there to the Moodle site. You can click on the demo first. That will help you save some time, and then you can also read the manual if you have time. Okay. But we'll be doing lab 8 this week on standing waves. Number 9, homework is due on Monday next week, and then on Wednesday, the 8th next week, we'll have our exam number 3. It will be the exam will be on the topics of electromagnetism, okay, and induction. So basically, it will cover the homework assignments from 7, 8, 9, okay? And then next week, because we'll have Easter Friday, so there's no Fridays lab section, so we'll cancel our lab for next week, okay? Then on the week coming back from Easter break, we'll have lab 9, okay? And then the last week, we'll have lab 10 before the final, okay? So that's what we have. The reminder items for the coming couple of weeks. Okay, so we'll get started on the lecture part here. Last time we talked about induction. So basically, if you have an inductor, which is a solenoid, we call it inductor in the circuit, okay? Or if you have a few coils in the circuit, then it actually react to the current change in the circuit. If there's current changing, either increasing in current or decreasing in current, then there will be inductions by the inductor, okay? Otherwise, if there's constant current, no increase in current, then there will be no inductions on the coil, okay? So in that case, inductor will have inductions if there's increase in current, okay? And the inductions is proportional to the change in current, okay? So it's given by this formula over here. The induced EMF is equal to the inductance times the change in current over change in time t, all right? And then because induced EMF is also equal to change in flux, so you can actually have two expressions for the induced EMF, okay? But if you set the later two terms equal to each other, then L is equal, or can also be calculated as equal to M delta phi over delta I, okay? You can change in the flux and then also change in current, so you'll be able to do that, okay? To calculate the inductance. And will be the number of turns of coils you have in a solenoid, okay? And we say if there's an inductor, if there's current going through the inductor, then there will be magnetic field produced, okay? That's what we learned earlier in the chapter. But anyway, if there's a magnetic field, then there will be energy stored in the magnetic field, okay? So the density of energy stored is equal to this guy, expressed in this guy. So energy by the magnetic field is equal to magnetic field square, okay? Proportional to magnetic field square. And then either multiply by all, you can treat as like divided by a constant number, okay? Similar to the electric field, the energy stored in the electric field, it's also proportional to the electric field strength square, okay? And then times a constant in that case as well. All right. And then we talk about if we have inductor in the circuit, okay? So we check inductor in a circuit along with a resistor. So then such a circuit is called an RC circuit, okay? It's similar, very similar to a RL circuit. It's very similar to an RC circuit, a resistor and capacitor combination in the in a circuit. Okay, so similarly in this case, but we are be looking at the current in this case because the inductor actually reacts to the change of the current. Okay, so in this case, if you close the switch, then the current will build up slowly. On the case of we have RC circuit, actually the voltage builds up slowly. Okay, so for RL circuit, your current builds up exponentially as a function of time, and then in this time, the tau constant in the exponential function here is equal to L over R. On the case of an RC circuit, we have tau constant as R times C. Okay, so that's the difference. Okay, so if you just join us, send a text message to us in the chat, say good morning or hi, whatever, so I can trace the attendance later. Okay, I heard someone just join us. Okay, so if you just join us, send a text message in the chat. I will trace that later for attendance purpose. Okay. All right. So this is what you have. So this expression is very similar to the voltage expression we got in the RC circuit. Okay. All right. So today we'll be checking on each of the elements we have learned so far, the resistor, capacitor, and inductor. Okay, so check these elements when they are in actually an AC circuit. Okay, so for this chapter, the content we have been dealt with so far is all with the DC circuit, direct current circuit. So starting from this point, this section will be checking on an AC circuit. Okay. So an AC circuit, whereas the circuit is powered by a alternating current, okay, power source. So this is the symbol you see as an AC circuit. Okay, so it looks like a sine or cosine function with a circle. That means the power source is an AC power source. Okay, because it changes signs. Okay, from time to time. All right. So if you have an AC source, then your voltage can be expressed in terms of a sine function. Okay, omega is the angular frequency, t is time, and then this is the peak value. Okay, now let's look at this most simple case, the simplest case, that when a resistor is being connected to an AC circuit. Okay, so according to Ohm's law, a resistor will follow Ohm's law. So VR, the voltage supplied to the resistor, okay, should be equal to the power source, and then should be equal to the current going through the resistor times its resistance. Okay, so that equals to I times R. So if V is a sine function, then I is also a sine function. It's simply VR over R. Okay, so in this case, so then VR peak value times the sine function. If you do the peak value in voltage divided by current, divided by the resistance, that gives you the current peak value times the sine function. Okay, so you can see if you have a resistor connected in the AC circuit, then your voltage is a sine function, your current is also a sine function. Okay, they are the same sine function, sine of omega t, sine of omega t, the same function. Okay, so if you plot the voltage and current at the same time on a graph, okay, versus time t, then you see voltage, all right, and current. Okay, so the magnitude here doesn't really matter. Okay, so sometimes your resistance is small, so then you can have larger current in magnitude versus the voltage. Okay, and then if your resistance is larger, then you usually get a larger V, okay, peak. But anyway, if you look at the two curves over here, so the same for the two is you have zero values at the same time. Okay, you have peak values for I and then VR at the same time. All right, and then you have minimums at the same time. Okay, so if that's the case, if they peak at the same time, then we call them in phase. Okay, so that means they peak at the same time, they minimize at the same time, they have zeros at the same time. Okay, so that's called in phase. Otherwise, we are called them out of phase if they don't peak at the same time, if the zeros don't appear at the same time, and the minimum that don't appear at the same time, then they are out of phase. Okay. So because the voltage and current, they are sine functions, so at certain time they are positive, certain time they are negative, okay? And then if you average either the voltage or current, because it's a sine function, so you can see the average will go to 0, all right? Now, but in order to describe the average power consumed by a resistor, then if you just use the average number, it doesn't help you much, okay? We can actually derive this, and I think it's in the coming slides, but a term that is very useful here to describe the average power consumed by a resistor would be called the RMS quantity, okay? We kind of learned this earlier in the electricity, and I think we also learned this when we are in thermodynamics, okay? So basically, if you have a sine function or cosine function, then the root mean square should be root mean square quantity of a certain quantity, say voltage, should be equal to, so if you square the voltage, and then if you take the average of that, should be equal to 1/2 of the maximum square, okay? Or root mean square quantity of that, this is equal to square root of this guy, okay? So that should be equal to 1 divided by square root 2 times maximum quantity, okay? Or equal to maximum quantity divided by square root of 2, all right? Okay, so let's take a look on the average power consumed by a resistor in this case, okay? So according to the Ohm's law and then the knowledge we learn in electricity, so a power consumed by a resistor is equal to I squared times R, all right? Now I is a sine function, it's I peak sine of omega t, so if you square that, gives you I peak square sine omega square and then times R, okay? So in this case, you can see then the average power, if we're looking at the average power, we take the average of this expression, okay? So the average of this expression, those two terms in front of the sine function, they are constants, okay? So you take them down as usual. But the sine square omega, it's a varying function, okay? So then if you take the average, you kind of plotted it over here, that's what you can do, and then you take the average, okay? So then this guy, because you square it, okay, sine is anything between -1 and 1. If you square sine function, it gives you something in between 0 and 1, okay? Then if you take average of anything between 0 and 1, you can actually get 1/2 of it, okay? So then your average power should be equal to, okay, so this guy, sine omega square, sine omega t square, average should be equal to 1/2. So then everything becomes 1/2 from here. So then your expression becomes 1/2 I square peak, okay, times R, all right? So in the previous slides, we see that if you do 1/2 of I peak square, it actually gives you I RMS square, okay? This you can check on the previous slides. So then your average value, you see the text in red here. So average power should be equal to the root mean square quantity square times R. Okay, so root mean square current square times R. All right. So compare this to the usual expression we had, like P equal to I squared times R. Okay, so then in an RC circuit, you can express the average power by R IRMS square times R. Okay, so we are going to use the root mean quantity to describe that. Okay, similarly, if you would use the expression we had earlier, the other expression for power, V squared over R, okay, so then you'll be doing the same algebra here. So because V is equal to V peak sine omega squared omega t, so then you square the V, so that it will be V peak squared times sine omega squared divided by R, okay? And then again, if you take average of the power, it's going to be the average from the sine function times the two constants in front of the sine function. It turns out to be 1/2 V squared peak divided by R, or V root mean square square, okay, divided by R. So again, if you do V square over R in this case, then you want to do the V root mean square quantity square over R, okay? Now the R, for the R, you don't do the root mean square because it's constant. It doesn't matter, okay? you only have root mean square quantity when the quantity is either in a sine function or cosine function. Okay. Similarly, you can prove that if you want to use P equals to V times I, then you want to use the root mean square quantities. Okay. So the average power will be root mean square voltage times root mean square current. Again, for the appliance we use at home, because the power source is AC source, okay? So then the specifications in the appliance, they are given all in root mean square quantity, okay? So voltage 120 volts in the US, that means the root mean square voltage is 120, okay? And then the current of certain appliance, if it's specified as say 1 amps, that means the root mean square current, okay? The actual maximum current could be higher, times multiplied by square root of 2, okay? All right, so that's what we have when you have a resistor in an AC circuit, okay? Now let's look at inductor, all right? So if you have inductor in the circuit, so then the moment you turn on the switch, okay, the voltage across the inductor should be the same as the voltage divided by the, or provided by the AC source, okay? But because the inductor will opposed to, because once you close on the switch, then the current is going to build up slowly. The inductor actually has the opposition to the current increase, okay? So then your current doesn't start at maximum value, okay? So if the voltage started at the maximum value, your current actually start from 0 and then gradually build up, okay? So if you plot the voltage and current going through the inductor on the same graph, you will see that the current actually will peak first, okay? And then, or the voltage actually peaks first, and then the current peaks later, okay? So there's a lag of peak values in current and then compared to in the voltage. So the current actually lags about 90 degrees, okay? If you look at this, the difference here, okay? Or it's actually 1/4 of the cycle. So each cycle, okay, you can see here, it's from here to here. So it lags by 1/4 of cycle, okay? And then if you express that in angle, okay, you can do the conversion, etc. You'll see that the lag in the angle is like pi/2 or 90 degrees, okay? So then we call that, if we express in angles, then it's called phase angle, okay, phase difference. So the current actually lags the potential by 90 degrees or 1/4 of the cycle, okay, pi/2. All right, so that's what you see, the reactions of the inductor to an AC source, okay? So in that case, we can still calculate what's the current by in the inductor. Okay, you can still do current equal to V over XL, because you can see the inductor has certain reactions to the voltage supply, just like the resistance does. Okay, but in this case, because for inductor, it's an inductor, it doesn't actually. If you look at the resistance of the inductance, okay, if you just measure it, and it will be 0, because in most of the case, or very close to 0, because the inductor is usually made just by pure metal. So then it has very high conductivity but very low resistance. Okay, for ideal inductor, it should have 0 resistance. All right, but as you can see, once you apply the voltage, the current doesn't go to infinity large, okay, at once. So there's a reaction there, okay? So for the current, if you want to compute it, then current should be equal to V divided by a certain number, okay? It's not 0, but it's a certain number there. And let's call this as the XL, okay? So this is the reactions of inductor to the AC power source, okay? So then we call this as the reactance, okay, of the inductor to the power source. And then if you have an inductor, we call it inductive reactance, okay? In the case of if you have a capacitor in an AC circuit, we'll call it capacitive Okay, reactance that we'll check in a couple of slides later. But for the reactance of inductor, XL, we use XL. For capacitor, we'll use XC. Okay, you'll see that. So XL is proportional to the frequency and then proportional also to the inductance of the inductor. Okay, so XL is equal to 2 pi frequency L or omega L. Omega is equal to 2 pi frequency. Okay, so in this case, then we can write the voltage supply to the inductor should be the source voltage, so peak value times sine of omega t, okay? And then if you divided this by the inductance, okay? So then you do voltage divided by XL sine of, because this guy, if we were looking for the current lags by pi over 2, okay? Then, so you want to minus pi over 2. Okay, so this is why you get expression for the current. Okay, it's also functions a sine function, but there's a phase shift. You just switch the move the sine function by certain phase change. Okay, phase difference 90 degree or pi over 2. All right, I heard someone just join us. So if you just join us, send us a text message in the chat. Say hi or good morning. So I will trace that later as attendance. Okay. All right. So let's take a look on the first example here. So we'll be looking at the reactance of inductor in AC circuit here. So you guys can go ahead and give it a try, and then we can look at the solution together in a couple of minutes. Okay, so but basically this one says if you have an inductor has a reactance of 100 ohms at 80 hertz. Okay, so for the reactance, it should have similar or the same units as a resistance. Okay, so for reactance, it has SI units of ohms. Okay, just as the resistance. Okay, I didn't mention that, but in case you are wondering what would be the unit for reactance, then it's also in ohms. Okay. It's asking you what's the induction of this inductor and what's the reactance of it at a higher frequency. Okay, give it a try and then we'll look at the solution together. All right, so let's take a look here. Okay, so this is a inductor in an AC circuit. So then it tells us the reactance. Reactance is second. Let me put my the other screen over here. So for the whoever watch this later can catch what we are seeing here on the paper. Okay, so for inductor, we use XL. Okay, it gives us this time is equal to 100 ohms. Okay, so for part A, and then the frequency is given as 80 hertz. Okay, now if we check the expression for or the equation for XL as 2 pi f times L. Okay, so we can calculate inductance because that's L, that's what we are looking for. So then we are looking for L should be equal to Lx or XL 2 pi f. Okay, so you always want to do 2 pi f here or omega. Okay, if you use omega, then keep in mind omega should be 2 pi times f. Okay, so this is equal to 100 ohms divided by 2 pi times 80 hertz. Okay, so this will give us 0.199 Henry. Okay, for the inductance. All right, now B says if you increase the frequency to 160, what will be the new inductance? So then you just use the new frequency, okay, but use the same inductance you have there. So 2 pi times 160 hertz, okay, multiplied by 0.199 Henry, okay, and that should be equal to 200 ohms, okay. Or if you know the relationship, if frequency increase, then by a factor of 2, then this should be also increased by a factor of 2. Then you can directly say it's going to be 200. Okay, so if you realize that way, all right. Okay, so this is the first one here. Any questions you guys might have? I'll pause for a few seconds. So unmute yourself and then ask me question if you have any. Okay. All right, so let's move on. Let's move on to check on the power consumed by inductor in an AC circuit, okay? So we can use one of the three expressions. We can use power equal to V times I. We can use power V squared over R, but in this case, because we are having an inductor, it actually doesn't have a resistance, okay? But you can do it the other way around, okay, later. But we are going to just use the one that is straightforward here, because for inductor there's no R here, so I'm going to just use P equal to V times I. All right, so V is equal to a peak value sine omega t. All right, and then I is equal actually going to be a cosine function because, okay, because I is equal to, because I is lagging the V by a factor of 90 degrees. Okay, so it's I peak is going to be I peak sine, as we saw earlier, omega t minus 90 degree. Okay, or pi over 2. Either way, or pi over 2. All right, but sine of omega t minus 90, okay, it's actually equal to cosine of omega t. Okay, so this is the relationship we utilize on the slide here. So then you can, we are not writing I as a sine function, we are just writing it as a cosine function. Okay, so then here we have V as a sine function, I as a cosine function. So sine omega t, cosine omega t, okay, you can do them multiplying each other there. It actually will give you 1/2 of sine twice of omega t. Okay, so then, so this is from geometry, the trigonometry formulas. So if you are not familiarized with this, you can check, do a review on that, okay? But the result will be equal to 1/2 V peak I peak sine of twice omega t, okay? So this is still a sine function, all right? So then if you are looking for the average power, you are going to average this expression, okay? The constants, they will stay, and then you just have to take the average for the sine function, okay? So average power should be equal to the constants times the average of the sine, okay? Now a sine, half of the time is positive, half of the time is negative. So if you average a sine function, it's going to give you 0, all right? In the previous case, when we look at the power by a resistance, so actually it's not a sine function, it's a sine square, okay? So it's a sine function, but you squared it, so it's positive. But this case, because it's just a sine function, so average will go to 0, okay? So this tells you that for an inductor in an AC circuit, actually the power it consumes is going to be 0, all right? So that tells you an inductor in an AC circuit, it doesn't consume any power, all right? It actually doesn't. So then for inductor in a AC circuit, actually it stores power, stores energy, okay? At a certain moment, it sucks in the power, but it stores it, it doesn't consume it. And then later on, it actually releases it, okay? So it's a good element here. It doesn't consume any power. All right. Now let's take a look on the a capacitor in an AC circuit, okay? So for a capacitor, again, if you look at the voltage and current, okay? So actually the moment you close the switch, actually the current is going to be maximum, okay? But the voltage on the capacitor actually builds up slowly. The current actually leads the voltage this time, okay? So in this case, it's the other way around, okay? So if you express the current in terms of voltage function, okay? So basically the charge on the capacitor, so it's going to be equal to C times V, okay, what we learned earlier. But the I should be equal to delta Q over delta T, okay? So then you can do that. You can do C delta V divided by delta T, okay? So then if VC is a sine function, okay, so then I should be a cosine, a sine function, but plus pi over 2, okay? So that gives you the expression like that. This says the current is leading the voltage by 90 degrees, okay, or 1/4 of the cycle. All right, so in that case, we can also say there's certain reactions of the capacitor to the power supplied, okay? So then for a current, we can also write in this fashion. So this will be very similar fashion of what we had for the resistor, okay? But we are not calling it the resistance because it's a capacitor. It's the reactions of the capacitor to the voltage. So we call reactance again, but this case we're referring to a capacitor's reactance. So we call it capacitive reactance, okay? We use X again, but sub C, okay, that denotes capacitor. Now in this case, okay, the reactance is different. It's 1/2 pi Fc, all right? In the previous case for capacitor or for inductor, it's actually, so it was actually, so XL is actually 2 pi F times L, okay? For XC is 1/2 pi F times C, okay? So notice the differences here, okay? So for inductor, it's proportional to the frequency and inductance. For a capacitor, the reactance is inversely proportional to frequency and inversely proportional to the capacitance, okay? So notice the difference here, right? Okay, and again, this guy would have a SI unit of ohms in ohms, okay? All right, similarly, we can check on the electric power consumed by a capacitor in an AC circuit, okay? So we'll be doing again just V times I, okay? So again, we can write the current as a cosine function because cosine of omega t plus 90 actually is also equal to cosine of omega t, okay? So if you are not familiar or you don't remember this relationship, you can again check on your trigonometry identities to remind yourself about that, okay? But this is what we get at the end, okay? So P then is equal to 1/2 the peak value in voltage, the peak value in current times sine of 2 omega t. Okay. Again, if you are looking at the average power here, then you are averaging this expression here. The constants stay. The sine function, you will take average of it. Okay. Again, sine function would have average equal to 0 because half of time it's in the positive region and then half of time is in the negative region. Okay, so then it average to be 0. So similarly here for a capacitor, it actually doesn't consume any power in an AC circuit. Okay, so that means it actually stores energy. Okay, which is a good thing. All right, so either capacitor or inductor will consume any power in the AC circuit. Okay, only the resistor consume certain power. All right. All right, let's take a look on a second example here on the capacitance. Okay, so this one says there's a 22 microfarad capacitor connected to an AC generator. Okay, so AC generator, that means it provides AC power. Okay, or AC power source with an RMS voltage of 118 and frequency of 60 Hertz. What's the RMS current in the circuit? Okay, so we can take a look at this one together, I think. Okay. All right, so on this one here, so I'm pulling out my little windows on this end here. Hope that you can see this on the video. Okay, later, if you didn't get a chance to write out anything, you may still be able to trace that, okay, in the video. So this one here, we are looking for what's the RMS current. Okay, so we are looking for high RMS here. All right. It gives us the VRMS, all right, 118 volts. It gives us C equals to 22.0 microfarad times 10 to the negative 6. The frequency is 60 Hertz, okay? Now for the current, for a capacitor, we say it's going to be equal to the V divided by XL, right? So for the current, normal quantity is equal to normal quantity. But if you are looking for RMS current, then you do RMS voltage divided by the reactance, or we are looking for a capacitor, so X sub C, okay? And X sub C, if you check the previous slide, you can see it's going to be equal to 1 over 2 pi F times C, all right? So okay, so then this is V RMS divided by 1 over 2 pi FC, all right? So then it becomes V RMS multiplied by 2 pi FC then, right? Because the numerator, denominator in the denominator becomes numerator, all right? So then this is 118 volts multiplied by 2 pi times frequency, okay, times 22.0 times 10 to the minus 6 farad. Okay, so your IRMS then is equal to, in this case, 0.979 in amps. Okay, if I plug in everything correctly in the calculator. Okay, so from here you can see your IRMS is equal to V multiplied to pi FC. Okay, so for B, it's asking you if you want to increase the current, RMS current, okay, what should you do about the adding a second capacitor in the circuit, okay? So because I is equal to V RMS 2 pi FC, okay? So if you want to increase I, then you want to increase your C, right? Now, if you get a second C in the circuit, okay, do you want to connect in series with the first one or in parallel in order to increase capacitance? Now, this is capacitors in series or in parallel. So if they are in parallel, the equivalent then is equal to C1 plus C2, okay? And this is in parallel. And then C equivalent will be equal to 1 over C1 plus 1 over C2. And then inverse if they are in series, okay? So you want to review the knowledge we learned earlier in the electricity. So now clearly, as you can see, if you want to increase this guy, then you want to take this expression, right? To add the second here, okay? And then on this one, you actually increase the capacitance. If you put them in series, you actually decrease, you actually decrease it, okay? So then this is the one you want to take, okay? You want to put them in parallel in this case, okay? So you want to put them in parallel and then connect them into the AC circuit, okay? Our power source doing it like that, okay? All right. So PHY is asking you if your target RMS is 1.5, okay, then what will be the value of the second one, okay? So we can use this expression, then you will be looking at the equivalent circuit here, equivalent capacitance here, okay, because we have two in combination, all right? So then once we figure out this guy, because the frequency is given, this is the new 1.5, we can solve for this one. Then once we have this one, we can take this number over here because C1 is given as 22, then we can solve for your C2, okay? So this is what we are going to do. We are going to solve for CEQ first from this guy. So CEQ then is going to be equal to IRMS divided by VRMS, okay, times 2 pi f, okay? If you go from there to there, you pretty much divide everything by V 2 pi frequency, okay? So then we are going to plug in the numbers this time. I is 1.5 amps, V is the same 118, 2 pi amp frequency remains the same. So then this gives you 33.72 microfarad, okay? It's going to be 33.72 times 10 to the minus 6, okay? But I use microfarad there. So then my CEQ is this guy, so 33.72 microfarad is equal to C1, which is 22 microfarad plus C2. So my C2 can be solved. Okay, sorry that I didn't get that in the camera. But C2 then, by solving this, it's going to be 11.72 microfarad, okay? So you can pick a second capacitor which has that capacitance and then put it into the circuit in parallel to the first one, okay? That's what you need, all right? Any questions you guys might have? Okay, I can pause for a few seconds for you guys to ask questions here. All right, if not, then we'll move on here. So after checking each of the elements in AC circuit, so then we'll be looking at them all together at the same time in an AC circuit, okay? So for example, if you have a resistance here, if you have a inductor here, if you have a capacitor here, okay? So you have three of them together in the AC circuit. We are going to just put them in series, okay, to each other. All right. So then we can treat the three elements as a collectively combination of them. So once you supply a voltage, okay, we can look at the current. If we treat them collectively, so then we can say there's a certain reactions of this combination to the power source, okay? Now, similarly to the to construct the Ohm's law for each of the elements, we are going to just call the collective reaction to the voltage to be the impedance, Z, okay? Because it's not resistance, it's not inductance, but it's actually a combination of resistance and inductance. So then we call it a different name called impedance, okay? Z in symbol Z, but Z should have the same SI units or ohms, okay? Because current equals to voltage divided by ohms, okay? And then So if you are looking for the maximum values, then you do the maximum values, okay, for I and the voltage. If you are looking for RMS values, then you are doing RMS voltage and then RMS current, okay. So this is what you have. Now let's look at what would be Z, okay, in terms of the RL and Cs, okay. So if we look at the voltage altogether, okay, so we know that for the resistor, the voltage is going to be the same as the power source, okay? It's going to be in the same phase as that. Now, for inductors, actually the voltage leads the current, okay? So a resistor, the voltage and current, they are in the same phase. And for inductor, the voltage leads by 90 degrees or pi over 2 or 1/4 of cycle. Now a capacitor, actually the voltage lags by 90 degrees or 1/4 of it, okay? So if you have combination of the two, then for these two, all right, they actually are opposite to each other, okay, by 90 degrees, and then this one is the same here, okay. Now this is something we actually don't have in this class, okay, but this can be mathematically proven by induce a quantity called phasor. So it's a vector quantity, okay. So if the two vectors, phasor is a vector, so then you can express the voltage on the resistor as a vector, and then on these two as vectors as well, okay. So the voltage on this guy, and then compared to the voltage vectors on these two, they are differ by 90 degrees. So that means the two vectors are having a 90-degree angles, okay. So if that's the case, then the overall magnitude is going to be equal to 1 square plus the second one, because on resistor or on the inductor and capacitor, they are actually in the opposite direction. They are differ by 180 degrees. So that means they are in opposite directions, okay? So then you want to take the difference of the two. All right, so then square. So this is coming from like the magnitude for a vector, okay? We are not going to go into details of that, but this is what you did, okay? So just keep in mind, if you want to derive this equation, it has to be done by introduce a quantity called phasor or a vector quantity, okay? So then this is what you have for the voltage, okay? Expression of that, all right. So if this is the voltage, then you look at this guy here, the voltage should be equal to I0 times Z, okay? So then you can see, you can equate this guy to this guy, okay? Put these two equal to each other. So then I0Z is equal to, for this guy, the voltage is I0 times R, okay? On this one is I0 times XL, on this one is I0 times XC, okay? So the I0s on here, if you do the squares, then the I0 can come out of the square root, okay? So it becomes I0 multiplied by this. So then you can see I0 here, and then I0 here can cancel out, okay? I0 cancel out, so then you have Z equals to square root of R squared plus XL minus XC squared, okay? You just need to know the final result here. For the impedance of a RLC circuit, then the impedance is equal to square root of the resistance plus the inductance or reactance from the inductor minus reactance from the capacitor square. Okay, so this is what you have to know. All right. And we will take a look on a third example here today. All right. Let me see. I think we are going to just have about the time to finish this one. So let's take a look at this one together, okay? So this one says find the RMS voltage across each element in the RLC circuit, okay? So in order to figure out the RMS voltage, so for RMS voltage on the resistor, I can write in that way, okay? It's going to be equal to the RMS current times the resistance. RMS on the inductor is going to be equal to the IRMS times the reactance of it, okay, according to the definition. And then RMS on the capacitor is going to be equal to IRMS times XC. because you have the RLC in series, so the IRMSs are going to be the same because the three are in series. Okay, the current is going to be the same. So then that means first you want to figure out the IRMS. Okay, now IRMS can be calculated by doing VRMS divided by Z, right? So this is from the definition of the impedance. Now impedance can be calculated by doing R squared plus XL minus XC squared. Okay, so let's do this. We need this guy first, so then we need to calculate. This is given, all right, and then we need to calculate this two first, all right. Those two XL should be equal to 2 pi F times L, okay. So then 2 pi times, so a lot of times people will forget about the 2 pi's. Okay, 2 pi times frequency, 60 hertz, times L, 28 times 10 to the minus 3 is millihenry. Okay, so then it's 10.56 ohms. All right. For XC it should be 1 over 2 pi F times C. Okay, the other way around. So 1 over 2 pi times 60 hertz, and then times 0.12 microfarad. Okay, so if you do that, it's going to give you 22,105 ohms. Okay, this is XC. And then R is given, so we can calculate Z. So Z is going to be equal to square root of R is given as 8.8 kilo. So 8.8 times 10 to the 3 ohms square plus XC or XL 10.56 ohms minus 22,105 ohms squared. Okay, so this would be 23,782 ohms. All right, now we have Z, we can calculate this guy here. So IRMS then is equal to 115 volts divided by 23,782 ohms. Okay, that will give you a small number, 4.836 times 10 to the minus 3 amps. All right. So then we have the I. We can calculate each of the voltages here. So VRMS on the R will be IRMS times R. Okay. So 4.836 times 10 to the minus 3 amps times 8.8 times 10 to the 3 ohms. So that's going to be 42.6 volts. Okay. VRMS on L is going to be equal to the IRMS as 4.836 times 10 to the minus 3 times 10.56 ohms. Okay, this will give you 0.0511 volts. Okay, a very small number on the inductor. VRMS on the C is going to be the I, the same I, times XC. XC is being 22,105 ohms. Okay, so that gives you 107 volts. Okay, now typically I would do a double check verification on my answers. Okay, because for the overall RMS is equal to the VRMS on the R square plus VRMS on L minus VRMS on the C, okay, square. So I would double check to verify my results, okay. So, and then this is given, so we know this is 115 volts, okay, on this side, okay. Then on the right-hand side should be also equal to 115, okay. So if we verify that, plug in the numbers, square root of 42.6 volts square plus 0.511 minus 107 square. And then it tells me it's also 115 volts, okay? So this side is this much, on the right hand side is also that much. Okay, so that means what I got for those three answers are correct. Okay, otherwise this wouldn't equal to each other. All right. Questions you guys might have on this one? All right, so if not, then I'll see some of you guys in the lab in this afternoon, okay? And the rest of you guys, I'll see you guys on Friday. All right, see you guys. Bye.